Okay, today we have an acetylene torch. It is stored at room temperature and is 500 kPa. And the flame is to be determined on how hot it burns at. Jeremy over here has...
Hello class, I today have a propane torch. The gas in here is stored at a mere 207 kPa, a little less than the acetylene over there, but we'll see what happens. And we're going to put it to the test of which is hotter.
So what we have are two shoes, similar shoes, and we are going to put them to the test to see which torch burns the shoe faster. Now, don't mind the fire in the background. We had a little fun first.
It's alright.
Now, we're going to get the torches ready, and then we'll be back. Okay, this is the acetylene torch. And this is the propane torch. Let's see what happens. Ready? Go. Over here. Winning. No, you're not. You're going down! Jeremy! Whoa! Okay, that is hot. As you can see, both the shoes have been completely demolished. From what I saw during all of this, mine in the acetylene burned at a more concentrated area than the propane. The propane having a bigger nozzle.
Yeah, and a more widespread area of affection covered more space.
But I believe that the acetylene had a more direct effect. Well, his just covered the entire shoe in flames, which this is still extremely hot.
This is getting, yeah, you can feel
Yeah, you can still feel the flames.
feel mine all the way up here.
Well, I mean, it's a pretty close competition. We'll have to go back and review the video
Number
before
crunch.
we actually figure out which shoe burned faster. So we'll get back to you, and hope you enjoyed it. Okay, after reviewing our footage and our calculations, we have come to find that our hypothesis was correct. The acetylene torch, which is at 500 kPa,
And the propane, which is at 207 kPa.
the acetylene will burn hotter.
Now, the propane actually burns at 2,237 degrees Fahrenheit, which is actually 3,800 degrees Fahrenheit lower than the acetylene, which burns at 6,000 degrees.
And remember, everybody, when using things that can cause bodily harm and injure people, always use protection. We came prepared.
Pause it. Hello, this is Jeremy Knipp reporting from the aftermath of what we just witnessed as our experiment. Now, I'm here in the studio, and after we plug and chug some different equations and variables of what we found, we've come up with this. So now, dealing with the properties of gas, gases are easily compressed because of the space between the particles. So, in our experiment, we had two gases. We had acetylene and we had propane. Now, since acetylene is compressed at 500 kPa, while the propane gas is compressed at 207 kPa, That led us to the understanding that the acetylene gas would burn hotter temperature because the gas inside of the container is so compressed inside the container that there is more kinetic energy going throughout it. So it would make it coming out at a higher pressure, making it hotter. Now, some other interesting facts we found: the amount of gas and volume and temperature are all factors that affect the gas pressure. Now, since the volume of the acetylene was constant and throughout the container, also with the propane, that would affect accordingly because it was all coming out at a constant flow. But since the pressure was higher in the acetylene, it would burn obviously hotter. On a side note, the perfect probably gas law that would affect our carbon experiment is the Gay-Lussac law. Now, since the pressure of the acetylene is higher than the pressure of the propane in its given container, this acetylene would burn hotter than the propane. Go to pause it. Pause.
There's 3 laws in this unit, and the first one is Dalton's law. Dalton's law is when you take the pressure of the total and then you separate that into the other pressures of all the other pressures of the ions. An example of this is when you take the pressure total and then you equal that to, say, 79.11 kPa, and then you add that to 21.22 kPa plus 0.04 kPa plus 0.95 kPa, and then you just add all that up, and then your total would come out to be 101.32 kPa. And this is an example of how you would set that up. There's the different kPas, which is the pressure, and then you would just add them all up, and there's your total right there. Yep. So that's Dalton's law. And then the next law that we're going to go over is Graham's law. Graham's law is when you take the rate of the first element that you would use and you divide that, or it's on top of rate of the second, and then you set that equal to the square root of the molar mass of B over the molar mass of A. So an example of this would be the rate of helium over the rate of nitrogen, and that's equal to the square root of 28 grams over 4 grams, and that's radical 7, which is 2.7 grams. So that's exactly how you do that. It's the rate of helium right here and the rate of nitrogen, and then that's 28 because the rate of nitrogen is 28, so you got to swap them, and then the rate of helium is 4, and that's equal to 7, or radical 7, and then it's 2.7. So that's Graham's law. The third and final gas law is the ideal gas law, and that's when you take the pressure and you multiply that times the volume, and that equals the number of moles times the rate times the temperature, and that's also together it's PB and RT. So in this problem, if you take 1.5 times 10 to the third kPa, which is now the pressure, and then you multiply it times 2.24 times 10 to the 6, which is the volume of the problem that we're using, and then that equals the number of the moles times 8.3 liters kPa, which is the rate, and 315 Kelvin, which is the temperature. In this formula and all the formulas, when you use temperature, the temperature has to be in Kelvin. It can't be in Celsius or Fahrenheit. So after you do this, you're going to solve for N in this problem because that's what it's going to ask for. And N equals pressure times the volume over the rate times the temperature, and that's 1.5 times 10 to the third multiplied times 2.24 times 10 to the 6th divided by 8.31, and then liters, pressure, and temperature have all been canceled out, so it's now left in moles, which is what you need for N, and that's multiplied by 3.5 Kelvin, and your answer after you multiply all that out is 1.28 times 10 to the 6th moles of CH4. And that's it.
Okay, this is Jeremy Knipp reporting after our experiment that you just witnessed out there. Now, I'm here to follow up with a report stating about what all we did and what we found in our experiment. Now, dealing with the properties of gas. Gases are easily compressed because of the space between particles in gas.
Pause it, Bridget. That was a horrible way to start.
this is Jeremy Knipp starring after our after. What the? No.
Because it went that
No!
way.
Hey! Ow! Stick's hot. Dude, it's just a sole. It's just a sole.
What?
Look, it's melting. My shoe is melting. Hey, look, I'm melting this with my shoe. Pick up your shoe. Don't fling it.
And I'm trying to pick it
Look,
up.
it's liquid fire.
I'll show you liquid fire.
Hey. Holy cow.
Oh, 1 second.
Holy. Look at
Mine,
this.
Mine folded on itself.
Pick it up.
I'm trying.
Holy crap. This is a heck of a fuel here. Maybe we should use this instead of gasoline. Pick it up.
I actually can't.
You can't?
No.
Dude, this is going in the water.
1 second. No, don't put it in water yet.
What, we'll let it burn longer?
Yeah, 1 second. I just gotta flip it.
Look at how big this flame is. The shoe's just falling apart.
Oh. There we go.
Oh my gosh. Hey, there we go. Cross the beams.
Oh, it's cray.
Ah, smoke.
Like it's falling off.
Yeah, it is literally falling off. This is ridiculous. Holy crap.
Hello, this is Jeremy. I don't